Yeah, good morning, Indian time, 10 o'clock in the morning. This is the last of the 2 or 3 live sessions that I was able to manage and join with you. And I have, I only hope that the experience of those of you who stayed with the course has been positive. And there are not many questions on the website. I've not seen very many. In fact, I've not seen any in the last couple of weeks. And all those questions which have been answered, I hope are answered to satisfaction. Hello, Krishna Agarwal. Yes. Yes, hello. How are you? You have to say something on the keyboard. Yeah, there are a few of you who are joining. The last week, which is the week coming up from Monday onwards, will have a little bit on the chemical bonding of diatomic molecules, polyatomic molecules, and also a brief introduction to the Huckel theory or the conjugated systems. One of the most beautiful theories in the early 30s to come up with, and with simple approximations to capture the essence of the resonance energy of benzene and many other aromatic compounds, as well as the aliphatic long chain compounds, but which are alternating single double bonded carbon atoms. So I would add a couple of lectures briefly on the Huckel theory and also the determinant, the Huckel determinant that you need to diagonalize and obtain the resonance energy. Yes, there is one more person, Anjali Krishna. Good morning. Yes, good morning, Anjali. And yes, if you have questions, please go on, type them. Yes, there is good question. Prasanta Das has asked me about, can you please give some physical insight about shift operators? Okay, first, mathematical definitions are possible. Physical insight, visualizability is something you have to be very careful. But if you talk about generally shift operators, okay, I hope you are referring to harmonic oscillator. Raising, lowering, or angular momentum, raising and lowering. And lowering operators. I hope this is what you mean by shift operators. If this is what you do, then shift operators are, first of all, not visualizable, in the sense they are not measurable. They are not measurable quantities. The reason is they are not Hermitian operators. They are, for example, in the case of Hermitian harmonic oscillator, there are two shift operators, A and A dagger, where the operators A and A dagger are Hermitian adjoints. Let me adjoints. What I can say is that these operators connect the possible transitions between different levels. For example, in the case of the harmonic oscillator, if the harmonic oscillator quantum state is n, and the quantum state is n+1, I have in mind an increase in energy like this. And perhaps, let me draw this again with 3 possible states. If you think about 3 states, n, n minus 1 and n plus 1. The shift operators A and A dagger connect to the levels between n and n minus 1 or n plus 1. So this is connected by A. This is connected by A dagger. But then please remember, if you are in this state and you want to excite the harmonic oscillator to a higher state, n plus 1, then the operator which connects these two states is the A dagger. This is the raising harmonic oscillator operator. If on the other hand, you are in an excited state n, and the system goes down to a lower state n minus 1, and then excites radiation, emits radiation, then such a state is connected by the lowering operator. This is purely the mathematical property that I can give. And the same thing with the angular momentum operators as well. You have the J plus and the J minus operators. And the J plus operator is connecting the state Jm to the state Jm plus 1. And the J minus operator connects the state Jm to Jm minus 1. So these are transitions introduced between different energy levels. And this will be very important in spectroscopy, particularly in magnetic resonance spectroscopy and electron paramagnetic resonance. The angular momentum states are connected to each other by these shift operators. And these shift operators are actually provided experimentally through radio frequency fields along specific axes. And the specific axis will determine whether you have a plus combination or a minus combination or a plus and minus combination to a Jx or a Jy, because Jx is nothing other than J plus J minus by 2. Okay. So this is the visualization I think is important. There is no other physical characteristics I am familiar. Let's look at if there are any other questions. Yeah, okay. Is there, okay, Krishna Agarwal wants to know about the examination. Sir, is there any question which would come in JEE from the chapter polymers? Oh, I do not know. I think what is important for you is the CBSE textbooks, the NCERT guidebooks, which you normally know as the teacher textbooks in your schools. The NCERT published books are the absolute basis for all of JEE questions. Usually there is very little outside in terms of the chapters or contents, but the level of questions will be slightly higher than what is there in the JEE textbook, in the NCERT textbook. Therefore, the answer to your question is, if polymers are covered in one of the physical chemistry chapters of NCERT, I think you must read them. Second, if you are only worried about whether there is a question on polymers and so on, the answer is from the NCERT textbook. Look into the polymer section, and that will definitely be important. But otherwise, I think polymers are extremely important because we use them day to day. I mean, including the shirts you wear, the materials you use, the plastics that you are being told to avoid, everything around you is on polymeric systems. So I think the basic chemistry is very, very important. Okay? So check with the NCERT textbook. Okay. Now, Pragya Pandey has asked, what is the hybridization of HCl? Actually, in the case of chlorine, it's a linear molecule. HCl is a linear molecule. Therefore, chlorine with the 3 p orbitals very nearly filled. That is, there are 5 electrons in the p orbitals, in the 3 p orbitals. And the s orbital energy of chlorine is quite far away from the p orbital energy. Therefore, I do not think that there is a hybridization associated with HCl or chlorine. Hydrogen is, of course, it's only one s orbital. Therefore, it's a straightforward, the Cl atom, one of the p orbitals, forming a sigma bond with the 1s orbital of the hydrogen atom. I think. Okay. Can you please attach some model question papers with lectures? That's a very, very good thing to ask. Yes, I think it is important for you. I have already given the examination papers to the NPTEL team. So let me see, today, tomorrow, you still have about 2 weeks, isn't it? I believe that the examination is on the 28th or 29th. Yeah, today is 14th. So I think it's on the 28th, Sunday. So you have 2 weeks. Let me do one thing. Within tomorrow, day after tomorrow, I will put in something like about 10, 15 sample questions from various chapters. They will not be directly from the question paper, which I have given already. Therefore, do not expect me to reveal examination papers ahead of time or even part of it. That's unethical. I cannot do that. But as you said, model papers, I think I'll give you a few problems. And also, this week, I cover the remaining part of chemical bonding, namely the homonuclear diatomic molecules, a little bit, very elementary things on the heteronuclear and the hybridization, and then the topic of Huckel's molecular orbital theory in some basic details. So for a course of 12 weeks, with starting from basic quantum mechanics to chemical bonding, I think there is a reasonable depth and also width for this course. So concentrate on every lecture that you have. And there will be some additional material at the end of this course for you to take home and for you to use in the future. Some lecture notes I would add. They are not directly important for the exams, but they may be important for your studies, higher studies later in quantum mechanics. I will add a few model questions. Okay. So other important things that I've not covered in this are, of course, what I call as a usual second course in quantum chemistry. The second course in quantum chemistry starts with the one electron wave function as a serious entity, and then from that to construct the many electron wave functions as a product of n, if there are n electrons, then n one electron wave functions. And then from the n one electron wave function, you obtain what is known as the symmetrized and anti-symmetrized linear combinations. For the electronic structure, the Pauli's exclusion principle states that we can only use antisymmetric combinations of the wave functions. The antisymmetry here means that the wave function changes signs if the coordinates of any pair of electrons is interchanged or interchanged. Then the wave function becomes a negative of the original wave function. So those things are usually the details for the next course in quantum mechanics. And then to define the one electron wave function as closely as possible in a collection of n electron systems, it is important to understand the approximation known as the Hartree-Fock approximation, the self-consistency of the electric potential and the electronic potential is important, and then the Hartree equations need to be solved. That's a starting point for a very rigorous ab initio quantum chemistry. From then, you go on to introduce Gaussian wave functions and other types of basis functions, later wave functions, and then in Gaussian, linear combination of Gaussian wave functions using the different types of orbital-like functions. Those are all usually parts of a more advanced course in quantum chemistry, and they also get you to the point of understanding the approximation methods more thoroughly, the perturbation theory method as well as the variational method. Okay. So, yeah, there are no questions, but it looks like the 3 or 4 names which I'm actually seeing in these sessions, you seem to be pretty regular. I thank you. I think it is important that you try and capture everything that is being done in the course. And congratulations that you have actually stayed through the 12 weeks. Even many of my students find the last 3-4 weeks, very difficult to continue on. Regular students in the MSc also. So I'm glad that some of you stayed. The other important thing that I have not covered in this course is the atomic structure. That is the structure of the electronic configurations of the atoms, with a lot of detailed explanation on what are known as the orbital angular momentum and spin angular momentum coupling of the electrons. Then the electronic shell structure of core electron systems, and the spectroscopy that excites core electrons, such as the Auger spectroscopy, X-ray photoelectron spectroscopy, and so on. Those are very important to understand the electronic structure and the electron densities of core electrons. So that's an important area. But usually atomic structure is very, very thoroughly studied in physics. Chemists do not worry so much about the structure of the individual atoms, that is, the electronic structure of the individual atoms, but start with molecular properties, because transformation between these different atomic electronic densities in various molecules is the problem of chemistry. Transformation between substances is the chemistry associated with that. And there are so many millions of molecules that chemists are always concerned with studying molecular structure, molecular transformation, and the quantum mechanics associated with the molecular properties, molecular understanding, and so on. Okay? Therefore, in this course, I also have not done the atomic structure, but a good course in the physics of atomic structure is given by one of my colleagues in physics. I would introduce him here. Yeah. In the NPTEL, you can look under the course of Professor Pranav Deshmukh. He is currently in the IIT Tirupati at present, but he was formerly a professor of physics in IIT Madras. This department, IIT Madras. I know this because I know that Professor Deshmukh has given several courses on some special topics, and also his research concerns with relativistic quantum mechanics, relativistic quantum mechanics of atoms. And I think he is one of the leading experts, world experts in the LS and JJ, that is a spin-orbit coupling and spin-spin coupling, total spin. JJ is total spin coupling, using the theory of relativity. So there are some elementary courses offered by him, and that will contain a considerable discussion on the atomic structure. The other, since you have been following this course, the other extremely important course that I think all of you would benefit from is the course on quantum chemistry by Professor Sebastian. I'm sure you already know Professor Sebastian, also from NPTEL. And Sebastian is a very, very good, a great teacher, in fact, and he's also the Shanti Swarup Bhatnagar prize winner in the early 80s, 90s, I believe. No, I would say, yeah, around early 90s. Professor Sebastian has a beautiful course of about 35 to 40 video lectures, and very thorough. So please when you have some time, look into the course by him, and you will find some discussions repeated, but a lot of other discussions complementary to what I have done more in mathematics here. But he has a lot of physical insight, and he uses the media, the multimedia quite effectively in some of these lectures. Okay. Pragya Pandey, sir, what are the elements of symmetry present in ethene? Okay. Since you have typed ethene, okay, ethene. You wrote ethene, so I believe it is ethylene. CH2 double bond CH2. Okay. H. Draw the structure graphically, and then you can see immediately all the symmetry elements present in them. This is a planar molecule, double bond, and there are three mutually perpendicular axes of rotation, what are called the C2 axis. Okay. One C2 is the C2 axis passing through the C double bond C. If you rotate the molecule with the hydrogen in plane, out of plane, hydrogen in plane around this bond, that's a C2. It's a 180 degrees axis. Okay. Then you have another C2 which is perpendicular to the double bond here, about which if you rotate again in plane, out of plane, 180 degrees, these two hydrogens go back to these two hydrogens position, and these two come to this hydrogen's position. So there is a second C2. And then there is a third C2, which is perpendicular to the plane of the board that you are in. I'm pointing out. So I would simply draw this as a drop. But if you remember in organic chemistry, this convention that something is out of plane, if you look at it that way. This C2, which is perpendicular to the plane of the screen, is a third C2. And then the ethylene also has the planes H, C, H, double bond C, H. The plane of the molecule is 1 sigma, okay? The plane of this. Then there is a plane which is perpendicular to the board. I would write the plane like this. Okay. Which is the other sigma plane perpendicular to this. And the third sigma plane is, of course, perpendicular also to the plane of the molecule, which is like this. Okay. So there are three planes which you call them as sigma xy, sigma xz, sigma yz. If you call the C2 axis as C2z, C2x, and C2y, the very fact that you have a C2z and a sigma xy means that the product of the two, namely the I, which is inversion symmetry, inversion takes this hydrogen to this hydrogen, and takes this hydrogen to this hydrogen, and it takes this carbon to this carbon. The coordinates are interchanged. I mean, the coordinates are basically changed to minus h minus x minus y minus z. That's what is the inversion. And you can see that the atoms interchanged to this position. Okay, so there are 7 elements, 3 C2, 3 sigma I, plus the identity. Therefore, the ethylene point group is D2H. Okay, next question. Vikas Rawat has asked a question: how to find the principal axis in a molecule? Good. Let me see. The z-axis, or one of the axes for the molecule, is often easy to find out. That's usually the symmetry axis of the molecule. So if you think about CH3, CH4, you know that it doesn't matter. It's a spherical top. So the axis system that you define, three mutually perpendicular axes, all three moments of inertia will be identical. But if it is the principal axis, essentially means the following. Okay, the moment of inertia I of a molecule is a tensor having components like this: Ixx, Ixy, Ixz, Iyy, Iyz, Izz. So what it means is that if you have a molecule with atom all over the place in three dimensions, first you find out the center of mass of the molecule, and then three axis systems. What you have to do is to mutually perpendicular to each other, and then calculate with respect to these axis system the position coordinates of each of the atom. Okay. I is equal to 1, 2, yeah. So these are the positions relative to the center of mass. This is the origin. This is 0, 0, 0. Okay. Once you know this, and each atom with a mass I, Mi, okay, what you do is to calculate these quantities. Ixx is equal to sum over I, Mi, Yi square plus Zi square. Likewise, Iyy is equal to sum over I, Mi, Zi square plus Xi square. And Izz is sum over I, Mi, Xi square plus Yi square. You see that Zz contains X and Y, Yy contains Z and X, Xx contains Y and Z. Okay. Then the off-diagonal quantities, what are called the Ixy component, is minus sum over I, Mi, Xi, Yi. Okay. And Yz is minus sum over I, Mi, Yi, Zi, and Izz is minus sum over I, Mi, Ixy, Yz, Xz. Sorry. This one is Xz, sum over I, Mi, Xi, Zi. Okay. Then what you need to do is to set up a 3 by 3 matrix in which you put these elements in this way: Ixx, Ixy, Ixz, Ixy, Iyy, Iyz, Ixz, Iyz, Izz, okay, and diagonalize this matrix. When you diagonalize this matrix, you will get three new quantities: I naught, which I would call as X prime, X prime, I naught, Y prime, Y prime, I naught, Z prime, Z prime, and all the other things will be 0. This is the way to determine the principal moments of inertia in a molecule from any arbitrary orientation. See, it does not matter how you assign your x-axis, y-axis, and axis. Put them in the center of mass, and then make sure that the axes are perpendicular to each other. Then you calculate the radius vector of each atom from that, give you the coordinates xi, yi, zi. All the atoms, and each atom has its mass. Then you simply calculate the mathematical quantities, diagonalize them, you get the principal moments of inertia. Okay, Prashanta Das, if there are two possible trial functions and both satisfy maximum values of E, but with different extent as compared to the ground state, which one would be the most suitable trial function? Okay, the question is to be slightly rephrased, Prashanta. You can choose multiple trial functions, but they both will not have, I don't know what is meant by maximum values of E. What you want to do is to calculate the energy E for each of the trial wave function, but the trial wave functions will be parameterized, will have a parameter in it, and the energy must be minimized with respect to that parameter. Now, I have not seen an example. I may need an example from you. If you ever come across, you can always write to me and send an email to me. I'll reply to you. I do not know of any specific instance in which two trial functions, arbitrarily chosen trial functions, will give the same identical energy E. I do not know of that. Okay. Maybe I'm missing something in the question. Let me think about it while I discuss this with other questions. See if I have an example of that somewhere. Okay. So let me go back to the window where okay, so these were all questions which were being discussed until now. Okay. So the question is, when there are two trial wave functions, both giving the same energy E. No, it's if the two trial wave functions are entirely arbitrary, they will not give you that answer. Therefore, if they both give you the same energy, then these two trial wave functions are actually equivalent to, they may be obtained from one from the other by a simple transformation, and therefore either of them would do. You don't need to choose any particular one. The spatial orientation of the function, which is closer to your physical picture, is all that you need to look at. I'm not clear on that question anyway, I must admit. Okay. So please send an email in a better way. I think that's the best thing, and I will respond to the email because some of you have followed my course quite independently, and I'm obliged to reply to you, maybe not on the same day, but probably within a day or two. So can I ask a question related to organic chemistry? Try. You can always ask a question, but I don't know whether you will get the answer because I don't think I understand organic chemistry as well as I would have liked to. But if it's a simple question, I would say yes. Otherwise, I would take this question to my organic chemistry student, my faculty, and send the same question by email to me, and you will get a reply from my organic colleagues who are much more distinguished than I am. Go ahead. Okay. So please tell us whether the strength of the sigma is greater than delta or not. I'll definitely ask my organic colleague to answer you. The delta, I guess you are referring to the sigma bond and the delta bonds. The general answer, as I can remember, is that the sigma bond is usually quite high in energy, and therefore you have to have a specific context in which the delta bond is likely to also be very important. If you have a molecule in mind where you have this problem, send me the detail. I'll definitely reply to you with the help of a colleague of mine. Okay? Generally, sigma bonds are the strongest bonds. By the way, it is Q related to physical than, okay, because you asked me earlier, that when transition take place, what are the conditions? Okay, if you are, yeah. Let me take the, give me a minute, I'll definitely answer the question. Question is, by the way, it is the Q related to physical than that when transition takes place, what are the conditions? So I need to change the screen. Can you just tell me about it? Okay, I mean, I'm trying to guess the question, what it is from, it's not clear. Yeah. What you are asking is if Q is the one that is related to transition, Q here is position. You are looking at harmonic oscillator, yes, position. Okay. Okay, in my symbol A and A dagger, they are actually related to Q. This Q is connected to some dimensioned variables times quantities times the A capital Q, and this Q is A plus A dagger by 2. Yes. Therefore, yeah, it is the Q which is related to transition. The transition is caused by between different levels, say n plus 1, and n minus 1. It is caused by the operator Q. It is caused by the operator Q. Since Q contains both of the raising and lowering operators, Q is the one. Therefore, the dipole moment matrix element is NQ M is non-zero if M is n plus or minus 1. Therefore, the state is connected to this state and this state. And obviously, if you have a whole series of things, so let me put n here and n minus 1 here and n minus 2 here, n plus 1 and n plus 2. Quite obviously, the Q connects only this, the nearby states, the two nearby states, Q. Q does not connect n to n plus 2, does not connect Q. In the same way, n is not connected to n minus 2 by Q. To connect n to n minus 2, you need an operator which is Q squared. Therefore, the dipole moment, which is proportional to the electric dipole moment of the harmonic oscillator associated with the molecular model, the dipole moment is proportional to the displacement Q, but the quadrupole moment, the higher electric moments, I wouldn't call it as quadrupole, I would simply call the higher moments, electric moments, are powers of Q raised to n. Therefore, the higher moments can connect to this. The other possibility is that if the harmonic model is not appropriate, if you have an unharmonic system, in the unharmonic system, the harmonic oscillator, the energy levels are only basis states. The wave function is basically a linear combination of all the harmonic states Ni, and therefore, if you have a wave function psi, and if you have another wave function psi prime, which is a different linear combination Aj and J, now you can see that psi and psi prime connected by Q, that is, these are unharmonic eigenfunctions, states of unharmonic eigenfunctions, they are connected by Q, then the selection rule delta n is equal to plus minus 1 does not apply. Delta n is equal to plus minus 1 as we have here. Okay? And here. That does not apply. So there are two instances when you will see non-Q related transition. One is that the higher moments of the electric moments of the system connecting the harmonic oscillator states will connect the multiple states, but these are usually very small in magnitude compared to the dipole moment. The other is that the molecular motion itself is highly unharmonic. Therefore, the wave function, the eigenfunction of the molecular eigenstate itself is a linear combination of harmonic oscillator states. And two such states can be connected by Q without the selection rule delta n plus minus 1. Yes, therefore the answer is Q is the one that connects the position operator is the one that connects the states and induces the transitions. Okay, oxidation state of H2O2. Well, the oxygen O2 2 minus. Therefore, the oxidation state of oxygen is minus 1 in each one of them. It's a peroxide ion, hydrogen peroxide ion. The peroxide structure is O bonded with O with the two hydrogens, and therefore the the O double bond, O single bond O itself is given a negative charge of 2 minus. So it is O2 2 minus, or each oxygen is 1 minus charge. Yeah, I mean, Pankaj Jindal explained that the Q is not for charge, the Q is the position, and yes, I have already assumed that it was the position operator and not the electric charge. Okay, so this time there are quite a lot of questions. They're all towards the end of the course. And so it is important to, and the second thing is, please, whenever you send me, this is an open invitation to all of you, those who have followed my course, I am quite happy to answer questions at any point of time. Just identify that you took one of my courses in the online MOOCs, and therefore you have had chance to look at some of my lectures. And if you have questions like this, please send it to me. Over a period of time, I'll definitely collect good questions and also put them up in my own website for others to have a look at, and I will also answer you. Okay? But it was good that you could actually take this course. I don't know how many of you are taking it for credit and how many of you are taking it because you just wanted to study. I do not have the statistics because I think your institution might be the one to tell you whether it's for credit or not. So it's about 10:44, okay. So we have another 15 minutes, 16 minutes. Okay. So let me continue. While if you have questions, I will keep explaining. Let me go back to the screen. So let me continue. The quantum mechanics that you are studying is, of course, the basis pretty much for all of the spectroscopy that you have to study later. And some elements of spectroscopy have been introduced to you here, elementary elements. In the harmonic oscillator, of course, you have already got an idea of what is known as the basic harmonic vibrational model, and therefore the infrared spectrum, assuming harmonic vibrations are very low energy vibration or vibrations at low temperatures. I mean, all of them amount to the same thing. In the case of angular momentum, of course, you have not explicitly seen the rotational motion and the microwave spectroscopy, but the algebra of angular momentum that is given to you in this course is important and is the basis for for understanding microwave transitions. And therefore, a lot of microwave spectroscopy depend on angular momentum associated transitions and changes in the angular momentum quantum number and so on. And then the spin which was introduced is already important in the electronic states in terms of singlet and triplet states of both the excited and multiply excited electronic states, and transitions between the singlet and triplet states, and what are called the forbidden transitions. All these things can be understood by understanding the spin wave functions and their properties. The entire spin-orbit coupling is, of course, is fundamentally the basic elements of the algebra of spin-orbit coupling have already been given to you. You have been given the orbital angular momentum description. You have been given the spin angular momentum description. Now you have to use that for multiple electrons, many electron systems, and so on. Okay. Let's see if there are any other questions. Okay, sir. Yeah, because is group theory totally related to linear and abstract algebra of mathematics? Well, the relation is something that we discovered as chemists and physicists. See, linear and abstract algebra in mathematics, see, mathematicians do come up with what are called abstract models. And very surprisingly, as it was, I think it was Professor Hardy many years ago, the man who discovered Ramanujan for the rest of the world. It was Hardy who said that mathematicians, when they discover something from the innermost self, I mean, I don't know the exact words, but he said that they are so conscious of the world. So whatever they discover eventually becomes very applicable to the real world. Okay. So in that sense, group theory, when it was discovered, of course, it evolved as a subject of its own inner beauty and connectivity and the properties of groups. But I believe, if I understand history a bit well, it was Professor Bragg and his teacher who had the first inclination that in X-ray crystallography, before Bragg, there was a very well-known physicist. These two first thought that group theory was probably important in understanding some of the symmetries of the molecular and the quantum mechanical systems. And it was later Professor Wigner, Eugene Paul Wigner, who studied this in much more detail with nuclear symmetry in mind. And in the case of chemistry and physics, there was a beautiful article in the 30s on point group from the solid state physics point of view, and also the space group point of view, which established all the molecular symmetry concepts. And of course, many chemists have always believed that the symmetry of the molecule and symmetry axis and symmetry planes that we can imagine have some property, and they found out that this was beautifully one-to-one with the elements of a group. And therefore, and these symmetry elements being discrete, the abstract group theory of discrete point groups became directly applicable to understanding molecular symmetry and the orbital nature. And once we have the mathematics of quantum mechanics come out with all the orbital properties, group theory naturally fit in to explain the properties of molecules. But please remember, chemists are by and large independent of the mathematical discussions and physics, the build-up that physicists have made through both mathematics and through experiments. Chemists are, by definition, they are benchtop people. Right? Most of us today, of course, there are a lot of us who are theoreticians who haven't gone to the bench very often, or probably never after we left our college and things like that, and who can talk about all the properties of the molecules without actually doing any experiments around them. But 50 years ago, I don't think a chemist could have survived without being in the laboratory and without doing experiments at the same time. Very few would have had any possibility of doing abstract the mathematical ideas. But the algebra of mathematics, this particular algebraic subject, turns out to be beautiful in applying the molecular orbitals, the symmetry concept to the molecular orbitals, and the molecular symmetry elements one-to-one with the group elements, and therefore the entire mathematical representation theory, as we call them in group, the group representation theory, involving what are called the irreducible representations, which are the most fundamental elements for the group representations. Relating the irreducible representations to the molecular symmetry elements was a beautiful concept by theoreticians. And in the current generation, one of the most well-known such chemists, is a Nobel Prize winning chemist many years ago, is Professor Raoul Hoffman in Cornell University. There are many others, of course, but yes, it is quite related to the symmetry of molecular systems is very thoroughly understood, and the symmetry-based rules for reactions have also been derived based purely on formal group theory, which is very nice indeed. Yeah, well, let me go back to the camera again. There's no question. Okay. Oh. This is it? Huh? Oh, camera. No, this is the camera, isn't it?
Yes.
Okay, this is the camera. So I teach group theory and applications in chemistry quite regularly to the MSc students. In fact, the next course in maybe a few months from now that I would like to launch is essentially the group theory from the mathematics, elementary mathematics, of course. I'm not going to do very, very high brow mathematics, representation theories, and so on, but relate the conceptual ideas. The most fundamental being the group, the great orthogonality theorem, as was so named or called by Professor Cotton in his very, very celebrated book on the chemical applications of group theory. Francis Albert Cotton, F.A. Cotton, I'm sure you know the book. So hopefully I will have some time to teach group theory with a fair number of animations and also the relations of these irreducible representations to the selection rules in spectroscopy, the selection rules that you have in crystal field theory, the selection rules that you have in the Woodward-Hoffmann and pericyclic reactions, and many others. The whole of space group is, of course, even more important when you study solid state and the solid state chemistry and the most beautiful structures that we are coming up today in three-dimensional world. So I will probably teach a little bit. We'll give some examples of this in the next course, maybe a few months from now. You will see the announcement in NPTEL when I do that. Okay. What is the best book for physical chemistry? There's no one single book, but I will give you a few books that I have thoroughly enjoyed, and here I'm going to do some advertising myself. The teacher who taught me my PhD, Professor Brian Sanctuary himself, he retired from McGill University Chemistry Department this year. This is Brian Sanctuary's book is called Leidler. Is a three-author book, Meissner and Sanctuary. Professor Keith J. Leidler, he's no more. He's the same Leidler that many of you are familiar with, his book on chemical kinetics. Leidler, Meissner, and Sanctuary produced a beautiful, what is called a highly animated and interactive textbook. It is expensive, but I'm trying to get into an agreement with Professor Brian Sanctuary to make some of these materials freely available to NPTEL. And if so, you will enjoy the most beautiful animations that were ever made in the whole of physical chemistry, this is a book simply called Physical Chemistry. I am biased. The reason being, this particular book, which is expensive, it's about 5,000 rupees or 4,500 rupees in Indian rupees, but it comes with a beautiful CD and has phenomenal number of animations chapter-wise. I don't think there is anyone who has done such detailed animated physical chemistry book. This is at the level of our BSc chemistry students and first year MSc chemistry students. Okay, this is for focused learning. The most thoroughly edited book is, of course, the book by Professor Atkins. And there are co-authors, I think it is Joanne. I don't remember the co-author, but Professor Atkins' Physical Chemistry. Very, very thoroughly researched. And every chapter having a huge number of problems, at least 2 or 3 different kinds of problems. Therefore, if you really want to teach physical chemistry to all audiences, as a teacher or even as somebody who wants to understand, must go through sections of this and at least be able to solve the first part of all the problems, every chapter that he has. The first part is sort of a recall and the simple applications of what is there in the textbook. The second part extends. There are 3 sections in the problems. The second section is slightly more advanced. And the third section takes examples from literature as well as numerical examples, programming and things like that, slightly more advanced. This, to me, is exhaustive. Okay. The last one, which I also liked very much, is the book by Donald Macquarie, and Simons. This is Physical Chemistry, a Molecular Approach, I think. Any one of these books, if you read from cover to cover, and if you are able to solve a large majority of the problems, will give you the skill as well as the understanding and the breadth that you can get from any other book at this level. More advanced level, then physical chemistry becomes specialized chapter-wise. You know, chemical kinetics, you have to study a book. Spectroscopy, you have to study a separate book. And solid state, you have to study separate. Those are now specialized areas. But to me, these 3, and of course, another very, very popular book that I have also used in my classes is the book by Professor Alberti, Silby, and Bhavandi. I think this is the name. It's also a physical chemistry. Professor Alberti is, of course, Daniels Alberti is, of course, a professor of physical chemistry from MIT, Cambridge. Silby, all 3 of them. But he is a senior author of physical chemistry. So, you asked for 1 book, I've given you 4 books. Pick up any one of them, but read them from cover to cover and solve all the problems in them. I think your level will be just as good as any other, the best in the world. So it's about 10:59. This is the last of the sessions. And surprisingly, today, there were also many questions of many different kinds. I guess you are thinking more about what to do and how to go on. And don't worry about the examination. The exams are usually some sort of a nuisance in the assessment process. But they have to be done when somebody needs to assess. Otherwise, I would like to give everybody who attempted the course as having completed the course, and your learning is your own. But the best of you, I will definitely try and invite you to IIT Madras to spend some time, hopefully in the future, if you also have the time, and tell us more about how you understood and what were the difficulties in going through this course, and what lectures could be done better. Obviously, the lectures in which I look much younger or obviously recorded a little older, they could have been done, but I was also short of time, and they contain the same amount of material. Therefore, I have put them in. But if there are any specific lectures that you think can be done better, you should also let me know. As teacher, that's the feedback that I would like to get from students. And all of you, wish you all the very best, and I hope you will continue to do physical chemistry and become some of the best chemists in the world. Thank you. Have a good day.